Bismillahirrahmanirrahim. Students, welcome to lecture 5. In this lecture, we will discuss some new topics, and that is here we see the topics covered in the previous lecture. We have covered up till the gain of the antennas. In this today's lecture, we will discuss the following topics: beam efficiency, the bandwidth, polarization, input impedance, antenna radiation efficiency, and antenna vector. Okay, beam efficiency. What is beam efficiency? Beam efficiency is the ratio of the power radiated within a beam to the total radiated power. That is P beam divided by P rad. So the mathematical equation for the beam efficiency is given by 2.54. Here we see that is the beam within that green angular range, and the angular span is that from 0 to theta 1, okay, on both sides of the z-axis. So this is the beam, is basically that conic section, and the power radiated within that beam is given by the numerator of the equation 2.54. that is the radiation intensity integrated over that angular span, and in the denominator we have the total radiated power. So the beam efficiency is that fraction of power within the beam. If, for example, this is an isotropic antenna, so isotropic antenna does not have a particular beam, so the total radiated power and the power within the isotropic radiation pattern will be the same, so the beam efficiency in that case will be 1. The next topic is the polarization, and the polarization is very important for antennas, because any antenna we see in the real world is designed for either linear polarization or circular polarization. Mostly the antennas are linearly polarized, but there are also some particular application like GPS and satellite application in which circularly polarized antennas are used. First of all, we have to define polarization. Polarization is the trace covered by the tip of the electric field in free space. It is the trace of the tip of the electric field in free space, or the path followed by the tip of the electric field or magnetic field in free space. We can define the electric field as a function of space and time. For example, let us assume that the electric field has two components, and that is x component and y component, and the wave is traveling in the negative z direction. Then the electric field can be written as Ez of t is equal to ax exz of t ay into eyz of t, where the ax is the unit vector along the x-axis and ay is the unit vector along the y-axis. Now, according to equation 2.5 in the book, the instantaneous components are related to their complex counterparts by this equation. So the x component can be written as real of ex ej omega t plus kz. So we multiply the phasor quantity with the time factor. That e raised to the power j omega t plus kz is the time factor. So we can transform from phasor domain into the space domain and time domain. So the general equation for the x component is ex naught cos omega t plus kz plus phi x, where ex naught and ey naught similarly are respectively the maximum magnitude of the x and y components of the electric field, whereas phi x and phi y are the relative phase angles of the x and y components of the electric field. So we will go step by step to find the tilt angle and the axial ratio of a particular wave. Here we see the rotation of the wave, that is the y-axis is the vertical axis and this the horizontal is the x-axis. So the y component is plotted along the vertical axis and the x component of the electric field is plotted along the x-axis. And if we see that as the wave travels as a function of time, right, so it traces a path. The path traced is here shown at the bottom of the figure, you see here. So this particular wave, you see, is x polarized because the path traced by that tip of the electric field, you see, is varying along the x-axis. So in this case the wave is particularly x polarized. Here is the polarization ellipse. The polarization ellipse is plotted, and you see that is the minor axis. OA is the minor axis of the polarization ellipse, and OA is the major axis of the polarization ellipse. And that is the EX is plotted along the x-axis, and the maximum value of EX is EX naught. Similarly, EY is plotted along the y-axis, and the maximum value is EY naught. And tilt angle is that angle which is the angle of the major axis relative to the y coordinate. That is the tilt angle of the polarization ellipse. Now we will find equation for OA and OB. So in the book we don't need to derive it, but it is given here that OA is given by this equation, which is dependent on the x values and the y values of the electric fields, as well as the phase difference between the x and y components of the electric field. Delta phi is basically here phi x minus phi y. It is the difference of the relative phases of the x and y polarized waves. OB is given by equation 2.67. Now the tilt angle of the ellipse relative to the y-axis is represented by the symbol tau and is given by this equation 2.68, which is equal to tau is equal to 5 by 2 minus 1 over 2 tangent inverse of this function in the bracket. When the ellipse is aligned with the principal axis, and that is possible only when tau is equal to odd multiples of 5 by 2, and the major or minor axis is equal to ex naught or ey naught, okay, and the axial ratio is equal to ex0 divided by ey0 or ey0 divided by ex0. Generally the axial ratio of the ellipse, which is also called eccentricity in mathematics, is the ratio of the major axis to the minor axis. So if the major axis and the minor axis becomes equal, if OA become equal to OB, the axial ratio will be 1. In that case the wave will be considered as circularly polarized. So the ellipse will be converted into a circle. If OA is maximum and OB is 0, that is no component along the x or y direction, the only one components of the electric field exist. So in that case the axial ratio will be maximum value divided by some minimum or 0 value, so it will be infinity, very large value. Very large value of axial ratio shows that the wave is linearly polarized. From the antenna coordinate system we can also find the sense of rotation, that whether it is the right hand or left hand. So if by the right hand we see if the finger shows the rotation of the tip of the electric field and the thumb shows the direction of wave propagation. So here we see that wave will be right hand circularly polarized or clockwise polarized. So polarization has main three types. Number one, that is linear. Number two, circular, and circular can be clockwise circular, which is also called right hand circular, or the circular can be counterclockwise CCW, which is also called left hand circular polarized. Similarly, elliptical polarized wave will have can be defined by an axial ratio, and that it can be clockwise or counterclockwise. Again, it will be either left hand or right hand. Now, generally, the polarization of a wave is elliptical. However, the two special cases are linear and circular. So the ellipse can convert to a line if either of the axes is missing. Okay. Or it can be converted to a circle if the one axis, the magnitude of the one axis is equal to the magnitude of the orthogonal axis. That is, OA become equal to OB. So that in that case it will become circular. So generally the polarization of the wave is elliptical. However, two special cases are linear and circular. Linear. So for linear there are three conditions. Number one, when the y component is 0 but the x component of the field is not 0. So in that case the wave will be x polarized, linear x polarized. Second criteria, if the y component is not 0 and the x component is 0, so in that case the electric field, the wave will be linearly polarized along the y direction. Third criteria is that neither x component is 0 nor the y component is 0. Both components of the electric field are non-zero. However, the phase difference, the relative phase between the x and y component, that is delta phi, is either 0 degrees or multiples of 5 degrees, 180 degrees. So if the angle difference is a multiple of 180 degrees or 0 degrees, then the wave will also be linearly polarized. So these three are the conditions for the linear polarization of the wave. Second, circular polarization. Circular polarization can be achieved if these two conditions are satisfied. First condition is the magnitude of the x component of the electric field is equal to the magnitude of the y component of the electric field. This should be satisfied. Both components should have the same magnitude. Second condition is the relative phase difference between the x and y component should be either plus 90 degrees or minus 90 degrees or multiples of plus 90 or minus 90. So if the phase difference is plus 90 degrees, the wave will be considered as right hand or clockwise polarized. Similarly, if it is minus 90 degrees, it will be left hand circular polarized. Third, elliptical. Elliptical polarization can be achieved. Generally, the wave polarization is elliptical, and it will be the condition for it is number one, that if the x component of the wave should not be equal to the y component, whatever the phase angle difference is. There is no restriction of the relative phase difference between the x and y polarized, but if one component is not equal to the other component, then the wave will be elliptically polarized. Second condition, B. If, for example, the x and y components are equal, which was the case for circular polarization, one of the conditions for circular polarization. However, the second condition will be false, which was valid for circular polarization. So the angle difference in that case should not be equal to plus or minus 90 degrees or its multiple if the x and y components become equal. So in that case, in condition B, the wave will be elliptically polarized. An elliptical polarization or circular polarization, both are measured by a parameter, and that parameter is called the axial ratio, which is the ratio of the major axis of the polarization ellipse to the minor axis of the polarization ellipse, OA divided by OB. So if OA is equal to OB, then axial ratio will be 1 and the wave will be purely circularly polarized. If OB is 0 and OA is non-zero, so in that case the axial ratio will be infinity, and it will mean that the wave is linearly polarized. So that is the summary. The mathematical equations have been discussed, and here is the description of the linear polarization in textual format and the circular polarization. So you can read this and here it is, that is for elliptical polarization. Okay, to determine the polarization of electric field or the wave, first of all, what we do, we have to represent the wave in space and time domain format. And the equation for the from space to time domain conversion is given, that is the red equation. You see that we take real of exyz. Exyz is basically the space domain electric field or phasor electric field. And if we multiply this phase domain electric field or phasor electric field with the time factor ej omega t, and then we take real of it, we convert it into time harmonic form, or you also call space and time domain format. Okay, so first of all we have to form the electric field, convert into exyz t form, time harmonic form. Then we plot the magnitude of that electric field as a function of time, and similarly we can also plot the phase of that electric field in step number 2 as a function of time. And this can be explained with the help of this example. In this example we see that an electric field is given E, which is equal to 2ax plus j2ay into ejkz. Okay. Now j term, which is iota, can also be written as e raised to power j phi by 2. It is the same thing. Okay, ej phi by 2 Euler identity, if it is simplified, it will give you j, because it is equal to cos of phi by 2 plus j sine of phi by 2, and it will be equal to j. E raised to power plus jkz shows that the wave is propagating along the negative z direction. If it was negative jkz, it would have been the wave propagation would be in the positive z direction in that case. However, in this case, it is in negative z direction. Now here we can see that the x component of the electric field can be deduced from this equation. So Ex is equal to 2 e raised to power j k z, and Ey, the y component, is equal to 2 ej phi by 2 into ej k z. We can combine the j terms. Okay, so it will become ej phi by 2 plus j k z. Okay. Now let us convert into time harmonic form. Okay, the first step is to convert the x component and the y component into time harmonic form, and the equation for that is, we see that we multiply the space domain electric field Ex with the time factor ej omega t, and then we take a real of this. So Ex is given. Okay, Ex is given, it was given by 2 e raised to power j k z, so it can be combined with ej omega t. So we got the term in the bracket, that is 2 ej omega t plus kz. Now this is Euler identity, so we will be left only with the cosine term. So we take real of this, it will be converted to cos of omega t plus kz. Okay. Similarly, for the y component in the time harmonic form or time domain format, take real of Ey into ej omega t. Ey was given by the in the previous slide, and combining with ej omega t and then taking real of it, so we got twice cos of omega t plus phi by 2 plus kz. And by using the trigonometric identity, that cos of alpha plus 90, cos of alpha plus 90 is equal to minus sine of alpha. So that trigonometric identity is used here. So the cos is converted into sine. So minus 2 sine of omega t plus kz. Now we can find the modulus of the total electric field, which is the square. We take the square of the x component and the y component in time domain format, and we take under the root. We see that both components values are given. Okay, simplify it. So cos square theta plus sine square theta is 1. 1 under root is 1. So the magnitude of the total electric field is 2. Similarly, we can find the angle. Okay, that is the relative angle between the y and x component. This is the polarization angle of the electric field. So tangent inverse of Ey by Ex, putting the values of Ey and Ex. So in the bracket we also get tangent of minus tangent of omega t plus kz. So tangent cancels out with tangent inverse. So we have got minus omega t plus kz. Now that polarization angle is equal to, for z is equal to 0, if we put z is equal to, it is equal to minus omega t. So the wave is varying at the rate, rotating at the rate of omega in the time domain format. Now, till now we see that is the two components of the electric field were Ex naught and Ey naught, both have the magnitude of 2, and the angle difference between the two wave components, that was delta phi, was 90 degree, which was phi by 2. J term was in the equation for the y component. So what is this? This shows that the wave is right hand circularly polarized, okay, or clockwise polarized in this case, and that is the angle psi, that is the polarization angle, or the vector. The electric field, the total electric field rotates. As it rotates in space, so this angle varies as a function of time, okay, directly varies as a function of time, and it is equal to minus omega t. The next term is the polarization loss factor. Polarization loss factor is also important when the polarization of the incident wave and the polarization of the antenna are not the same. So in that case, the antenna will not receive power from the wave. Okay, so the reception quality or the link will be very loose. So in that is the polarization loss factor is mathematically defined as the dot product of the polarization wave, polarization of the incident wave. So rho w is the polarization of the incident wave, and rho a is the polarization of the antenna in the transmitting mode. So the dot product of the wave polarization and then the antenna polarization, and then we square it. So that is the mathematical definition of the polarization loss factor. It is also equal to cos of psi p whole square, and that psi p is the angle between the wave polarization and the antenna polarization vectors. So for example, if antenna, and in order to find the polarization loss factor, the antenna polarization is determined in its transmitting mode given by rho a, and the polarization of the incident wave is determined in the direction of the wave travel, that is rho w. So polarization loss factor can vary from 0 to 1. Okay. 1 means that 1, it will be 1 because if the unit vectors are the same. If the polarization of the wave and the antenna is the same, then the polarization loss factor will be 1 because the dot product of similar unit vector is 1. So there will be no losses, okay, due to polarization mismatch. However, if it is 0, because if the wave polarization, let's say, is x and the antenna polarization is y, so two different unit vectors, the dot product will be 0. So in that case, the polarization losses will be maximum or equal to 0. PLF will be 0 in that case. Now we can also convert the PLF from dimensionless mode to the dB mode. So taking the dB 10 log of 10 of that PLF, so 10 log of 0, log of 0 is infinity, so it will be minus infinity, and 10 log of 10 of 1, log of 1 is 0, so that will be, and dB scale, it will be 0. So if PLF and dB is 0, that means that there are no polarization losses, and the angles are shown here. You see here, that is the relative angle of the polarization of the antenna with respect to the horizontal axis, that psi angle, and psi p It is the angle between the polarization vector of the wave and the polarization vector of the antenna. So using antenna polarization in the transmitting mode and incident wave polarization in the direction of wave travel, correct polarization loss factor will be given by this equation. Now using this equation, what PLF will be maximum if the two unit vectors are similar. That means if clockwise and clockwise or counterclockwise, means that if the wave is right hand or clockwise polarized and the antenna is clockwise polarized, then the PLF will be maximum, and in that case the polarization losses will be minimum. There will be no polarization losses. However, if this condition is not satisfied, if one wave is clockwise and the antenna is polarization is counterclockwise, in that case the polarization loss factor will be minimum, 0, and there will be maximum losses due to polarization mismatch. Now the concept of the polarization loss factor can be simplified, can be explained with the help of these. Now let us take this example 2.11. The electric field of a linearly polarized electromagnetic wave is given by EI is equal to AX E naught XY e raised to power minus jkz. So it means the wave is propagating along the positive z direction. Its maximum value is x naught, e naught, and the polarization is x polarization of the electric field, incident electric field. Now this wave is incident upon a linearly polarized antenna whose electric field polarization is expressed as follows: EA, that is the electric field of the antenna, is equal to AX plus AY into ER theta phi. Now here both X and Y components exist. Okay, we have to find the polarization loss factor. So polarization loss factor, the formula is the dot product of the unit vectors of the wave polarization and the antenna polarization. So first we have to find the polarization of the wave. The polarization of the wave is given as X polarized, which is equal to rho W is equal to AX unit vector, and for the antenna the polarization of the antenna is given by AX plus AY under the root 2. Okay, so this is the total polarization of the linearly polarized antenna. Now the polarization loss factor can be found if we take the dot product of these two unit vectors and then we square it. So take the dot product. So dot product will give us only one value, which is 1 over under root 2, and taking square of the 1 over under root 2, so that will give us 1 over 2. So 50%, that is 50%. So it means the antenna will receive 50% of the power. The 50% of the power will be lost due to the polarization mismatch. Okay, so which is in dB equal to minus 3 dB. If we take 10 log of 10 of 0.5, so that will give 0.5, 10 log of 10 of 0.5 give us 0.3, okay, minus 0.3. So that will be equal to minus 3 dB. Another example will explain the concept even further. Here it says that a right hand clockwise circularly polarized wave radiated by antenna. Okay, so the antenna in the transmitting mode radiates a wave of right hand circular polarization placed at some distance away from the origin of the spherical coordinate system, is traveling in inward radial direction at an angle theta phi, and it is impinging upon a right hand circularly polarized receiving antenna placed at the origin. So this is a tricky question. Means that a right hand circularly polarized wave radiated by antenna placed at some distance away from the origin of spherical coordinate is traveling in inward radial direction at an angle theta, and it is impinging upon a right hand circularly polarized receiving antenna. So if in the receiving mode the polarization of the receiving antenna is right hand, so it means in the transmitting mode it will become left hand. So that is the trick here, because according to the definition of the polarization loss factor, we have to determine the polarization of the wave in the direction of the wave travel and the polarization of the antenna in the transmitting mode. The polarization of the receiving antenna is defined in the transmitting mode as desired by the definition of the IEEE, assuming the polarization of the incident wave is represented by this. Okay, so EW is equal to A theta plus J A phi and some general value of electric field. So theta and phi components exist. So this is a right hand circularly polarized incident wave. Now the magnitude of the unit vector can be found, which is given by this. Rho W will be equal to A theta plus J A phi divided by under root 2. This under root 2 comes from 1 square plus 1 square under root. So it becomes under root 2 by the basic theory of vectors. We can find the unit vectors. While that of the receiving antenna in the transmitting mode is represented by the unit vector. So in the receiving antenna will be in the transmitting mode will be left hand CP. So that way the polarization of the antenna will be become opposite to that of the wave. You see here, that is A theta plus J A phi divided by under root 2. So the imaginary term will become negative. So A theta minus J A phi divided by under root 2. What does it show? It shows that the angle for the wave, the relative angle between the theta and phi components will be 90 degrees. So that means right hand circular polarized, and for the antenna the relative angle between the theta and the phi components in the transmitting mode, the polarization will be left hand because the angle will be minus 90 degrees here. Now you can find the polarization loss factor by taking the dot product of the two unit vectors. So that is rho W dot rho A whole square. It will give us 1 plus 1, okay, whole square. So that is 1 over 4 into 4 and 1. So the polarization loss factor will be 1 or 0 dB. It means that the polarization of the incoming wave matches the polarization of the receiving antenna, and there should not be any losses. So the polarization loss factor is 1, so there are no losses. Obviously the answer matches the expectation. Now let us take an example of the circularly polarized antenna given in the book. So here in the book we see a cross dipole, or this cross dipole is also called turnstile antenna. We see here that this is a cross dipole, basically two dipoles. That is, one is the horizontal dipole and then the other is the vertical dipole at 90 degrees to each other. Okay, they are fed or excited by two coaxial cables, okay, going to each dipole, and that is the input power is coming from a common connector. Okay, so the power is split into two equal halves, okay, two equal parts, and then it goes to the antenna, the cross dipole antenna. Here the ground plane is also shown here. The ground plane is connected in order to get maximum gain, to increase the gain of the dipole antenna. And you see that so each dipole gets equal magnitude of power. That means one dipole is along x-axis, so the value of Ex will be equal to Ey, and that is the first condition for circular polarization. The second condition for achieving circular polarization is that the phase difference between the x and the y component should be 90 degrees. So that is achieved by this phase shifter. The phase shifter is connected at the input of the antenna. So this phase shifter will introduce a phase delay of 90 degrees or a phase advance of 90 degrees in order to achieve left hand or right hand circular polarized waves from the antenna. Okay, and the distance of the reflector, the ground plane, from the dipole is lambda by 4. So this dipole, cross dipole antenna will be designed for some frequency or wavelength lambda. So that is the distance from the dipole will be lambda by 4 here. And that is important because if it is at a distance of less than lambda by 4, then the radiation pattern of the dipole antenna will be distorted. It will not be omnidirectional, but however it will become distorted. Now the connections are straightforward. that the outer conductor of the coaxial cable is shorted to the ground plane, and the inner conductor of the coaxial cable are connected to the dipole elements. To further explain the concept, the design and understanding of the circular polarization, I will upload a very basic paper, Understanding Circular Polarization, which is in which a cross dipole has been designed, and you can test that in CST Microwave Studio. You read the paper, implement that cross dipole, and you will get similar results. Okay, that's all about the above mentioned topics. If there are any questions, please ask.